Imagine you're a brilliant astronomer in the 15th century. You look at the night sky and see the sun, moon, and planets all gracefully circling the Earth. Your models, your math, your entire worldview confirms it. But there are a few nagging problems, planets that seem to move backward for a bit. You invent complex workarounds, little loops called epicycles, to make the math fit. You're not wrong. You're just doing what all great scientists do, solving puzzles within the accepted rules. But what happens when the rules themselves are the problem? This is the central question in Thomas Kuhn's groundbreaking book, The Structure of Scientific Revolutions. Published in 1962, it completely overturned our popular idea of science as a steady, linear march toward absolute truth. Instead, Kuhn reveals a much more dramatic, human, and revolutionary process. The book has three core ideas. First, that science operates within powerful frameworks called paradigms. Second, that science goes through long periods of calm, normal science, punctuated by intense crisis. And third, that real progress happens through paradigm shifts, radical revolutions that change the world. So, what's a paradigm? It's not just a theory, it's the entire operating system for a scientific field, the shared assumptions, methods, and even the unspoken rules about what questions are worth asking. For centuries, Newtonian physics was the paradigm. Scientists weren't trying to disprove Newton, they were using his laws to solve fascinating puzzles, like calculating the orbits of planets or the path of a cannonball. Kuhn calls this normal science. It's incredibly productive, but it's all about working inside the box, not thinking outside of it. But sometimes the puzzle pieces just don't fit. A result appears that the paradigm can't explain. This, Kuhn says, is an anomaly. At first, scientists might ignore it or tweak their theories to make it go away. But when anomalies start piling up, the field enters a state of crisis. Confidence in the old paradigm shatters. The rules no longer seem to work, and the scientific community becomes divided and uncertain. A great example was the orbit of Mercury. It didn't quite match the predictions of Newton's laws, and for decades it was a nagging anomaly that couldn't be explained away, sending physics into a quiet crisis. This is where the revolution happens. A crisis opens the door for a completely new paradigm to emerge. And here's the juicy part. The new paradigm doesn't just add to the old one, it replaces it. It's a total worldview change, what Kuhn calls a paradigm shift. Think of the switch from Newtonian physics to Einstein's theory of relativity. Einstein didn't just tweak Newton's math, he fundamentally redefined space, time, and gravity. Suddenly, Mercury's weird orbit made perfect sense. Kuhn argues these shifts are like a religious conversion. They're not purely logical. Scientists who grew up with the old paradigm often can't make the leap. They are quite literally seeing a different universe from those who adopt the new one. In the end, the structure of scientific revolutions teaches us that scientific progress isn't a smooth accumulation of facts, but a series of brilliant, messy, and world-shattering upheavals. It reveals that science is a deeply human endeavor, shaped by communities, beliefs, and a resistance to change right up until the moment that change becomes unavoidable. The key takeaway is that after a revolution, scientists, as Kuhn put it, work in a different world. If you found this fascinating, you might also enjoy Karl Popper's The Logic of Scientific Discovery for a contrasting view, or Daniel Kahneman's Thinking Fast and Slow to explore how these mental frameworks shape our own daily decisions. Find more great summaries and reading guides at booksplat.com. Level up yourself today, 3 minutes at a time.